For our last lesson on graphing, we're going to look at how to graph the tangent function, as well as its reciprocal, the cotangent function. First, for the tangent function, to go over some of the differences with the other functions we've looked at, the period formula has changed. It is no longer 2 pi divided by b, it is now just pi divided by b. That means this graph is going to be half as wide, so it will not use up as much space horizontally. So you'll see that that means my tick marks have been labeled a little bit differently because I didn't want to waste a lot of space on the side. So now I have more room to stretch out the x values I've used. The important starting values to use for your tangent function are listed here. So in fact, it's actually usually easier to start from the middle as far as plotting. You have the dot 0, 0, pi over 4 for the x value, and a y value of 1. That would be this dot right here. And then whenever you see undefined for the y coordinate, that x value has an asymptote. So that's where you would actually want to change colors and then draw a vertical dotted line. And then we can do the same thing on the opposite side. Negative pi over 2 would be the one on the fourth square here to the left. And negative pi over 4, negative 1 would be this first tick mark here, that first pair of boxes. So you end up with these 3 dots and a pair of asymptotes if you're following these starting coordinates. And then you could fill in more dots. These are the only ones I'm really going to be looking at as far as grading for assignments and tests. And then some people struggle with how to draw the shape of the tangent graph, but just pretend that you're drawing a parabola that opens up, but we're only going to draw the right-hand side of it. And then do the same thing. Imagine a parabola that's facing down, but we're only going to draw the left-hand side of it. Because sometimes students end up with too many wavy motions, or they end up causing too many turns and bends in their graph. So just think of a parabola up and a parabola down, but you're just drawing one half of it. So this is one period of the tangent function. Generally on tests, I will have you draw 2 periods, so we can always copy and paste this image over to the sides as well. But this is one full image of the tangent graph based on these starting values here. I also want to show you where these numbers are coming from. So I'm going to refer to the unit circle for this next part, and we'll pay attention to the coordinates of 0, 0, pi over 4, 1, and pi over 2 undefined. So as with the other functions, those starting coordinates I'm giving you all come straight from the unit circle. So our x coordinates on the unit circle, or our x coordinates on the starting points, are our radian measurements, our angles here. So we have the values 0, pi over 4, and pi over 2. And then our y coordinates are the values I have listed for tangent, since we're drawing the tangent graph right now. So I have the coordinate 0, 0, pi over 4, 1, pi over 2 undefined, and you can keep going. If you have 3 pi over 4 marked on your graph, you would have 3 pi over 4 negative 1, and then you would have pi 0, and it just keeps going around the unit circle the exact same way. Now the reason I block out these, the pi over 6 and the pi over 3 lines is because those have y coordinates of square root of 3 over 3 and square root of 3. Those aren't dots you can really draw precisely on a graph anyways, so I just ignore those lines and only focus on the ones that are on the x and the y axis, or the ones exactly halfway between. So if you ever forget the numbers that I have listed here in the table for your starting points, then remember that you can recreate them by using the unit circle to find 0, 0, pi over 4, 1, pi over 2 undefined, and etc. Now we'll look at the standard cotangent function, or the parent function for cotangent, because remember, we are going to start moving these values with transformations coming up in a moment. So again, I have listed a series of starting values for you to use. And be especially careful of the fact that my x values have changed. Since cotangent is the reciprocal of tangent, that causes a change on where our asymptotes land and where our x-intercepts land. So now we're actually more interested in the values from 0 to pi, which means I'm not going to be going around the origin. I'm actually going to be having one asymptote go through the origin. And then while I'm doing this color, I'll go ahead and do the other asymptote as well. Your second asymptote happens out here at pi. Then for the actual dots I'm drawing, I said at pi over 4, we should be at a height of 1. And at pi over 2, we should be at a height of 0. And 3 pi over 4 should be at a height of negative 1. Now the other thing you'll notice about the cotangent graph compared to the tangent one went up on the right-hand side. The cotangent one has flipped that around. So now it's going up on the left-hand side. But again, I'm going to imagine a parabola. I'm just going to draw the one half of it. And then another parabola, I'm going to imagine drawing down, but I'm only going to sketch the right-hand side of it. So luckily, the tangent and cotangent graphs are fairly similar. They have very similar shapes to them anyways, but be especially careful about the changed location of the asymptotes and the fact that the graph is upside down. So next we'll look at applying transformations to these shapes. For the first example, we're going to look at the first tangent function, the regular tangent function, and we're going to be multiplying the y coordinates by 2. And then because we have a number subtracted inside parentheses, we're going to be shifting all the dots to the right a length of pi over 2. Remember, this is backwards from what you expect. So the fact that I see a minus means this is a horizontal shift to the right pi over 2 instead. Now, how many squares or tick marks over pi over 2 is, that will change from one question to the next. This is the standard scale I use for tangent. So if you didn't change it, that would mean that you want to move things to the right 4 boxes in this case. So look at where the regular tangent starting dots are. For example, there's usually a dot at 0, 0. If I multiply that y coordinate by 2, I still have a height of 0, but then I'm going to move it to the right 4 boxes. So I end up here instead. Next, there's usually a dot at the first tick mark and a height of 1. I am multiplying that y coordinate by 2, so now it's at a height of 2. And then I am moving it to the right 4 tick boxes. You could also do the dot that usually starts to the left 1 tick mark and down 1. This height is getting doubled, so negative 1 times 2 is negative 2. And then I am moving it to the right 4 boxes to end up here. The other objects we need to fill in are the asymptotes. Now for the asymptotes, you don't have to worry about the vertical motion. If there's any vertical stretching or vertical shifting, you don't have to worry about it. You only have to do the horizontal stretches and shifts. So in this case, I need to move the asymptote that used to be on the second tick mark. I have to move it to the right 2 tick marks. Also, if you already have the dots drawn in, everything should be very consistent and uniform in terms of distances and lengths. So I have everything based on 2 squares over, something else happens. 2 squares over, something else happens. 2 squares this way, something happens. 2 squares this way, something happens. So you should end up with a very symmetrical graph in the sense that you don't have different lengths horizontally between one dot and the next. Now that I have one period kind of outlined, I'm going to go ahead and set the next one too while I still have the asymptote color out. So I can see that altogether it's 1, 2, 3, 4 tick marks across between asymptotes. So it should be the exact same thing all the way throughout the graph. I'm just copy and pasting that image. And then if I switch back to the original color, I know that the same thing would happen with the dot that's halfway between the asymptotes. Is that a height of 0? On the right-hand side of that dot, it was a height of 2. On the left-hand side of that dot, it was a height of negative 2. So I should end up with 2 very similar shapes. And as far as actually sketching the curve through them, this is a parabola opening up. And this is the half parabola opening down. And I'm just duplicating that here. So here I have shown 2 full periods. Most important thing for checking purposes being the location you have the dots drawn at and the locations of your asymptotes. I would need to be able to read on the scale what x and y values you have for each of the objects indicated. For this example, we're using the cotangent function, so the second parent function we looked at, and I have the harder transformation being applied here, the horizontal shrink. Remember, it's backwards from what you expect, so 2 times, it's actually the reciprocal of that. It's actually half as wide. And then this transformation is going to move all of our dots down 1. Now to take care of the horizontal stretches or shrinks, I don't actually try to figure out how far to move the dots left to right in this case. I actually just change my scale. And I know these numbers look difficult, so let me help you with where they are coming from. First, I found the period, which is the absolute value, or pi divided by the absolute value of b. And remember that this is different from the formula we use for the other 4 functions, the sine, cosine, secant, and cosecant. It's not 2 pi, it's just pi over b. So I got pi divided by 2. The absolute value didn't actually change anything here. And then I take that length, that's how long the entire graph will take to repeat, but I'm dividing it by 4 because I want to break that up into 4 different tick marks. So if the full graph takes pi over 2, I want to split that into 4 equal pieces. Writing divided by 4 or times 1/4, it's the same thing. I got pi over 8. So this is the distance between tick marks. So then each of my tick marks came from doing 1 times pi over 8. For the second tick mark, 2 times pi over 8, but I reduced the fraction. For the third one, I did 3 times pi over 8, which does not reduce. And then for the last one, 4 times pi over 8. So that was the 4th tick mark. Now I can actually just pretend I'm still drawing the same basic starting points for the graphs. I'm just ignoring that they're happening at different x values. So that takes care of my horizontal stretch or shrink, which means I'm going to kind of pretend I'm drawing the graph normally. I've just changed the scale instead, but I am going to shift the dots down a length of 1. So for the tangent function, remember this one usually has an asymptote at the origin. So our starting point is not at the origin for the cotangent graph. It actually starts out at the second tick mark. And then I'm moving that dot down a length of 1, so it ends up here instead. The other important thing to remember for this graph is it doesn't go up on the right side, it actually goes down on the right side. So the dot is going to be one below down here, and on the left-hand side it's the opposite, it's actually going to move up on that side. And then that means I would have my asymptotes just at the edges. So one more tick mark over in both directions. By changing my scale, that means I'm still using 4 tick marks across for my next asymptote. And then for getting my second period filled in, to copy and paste this image over, halfway between the asymptotes was at a height of -1. On the left side, it went up 1. On the right side, it went down 1. And then I can just sketch in the parabolas, the half parabolas rather, passing through those dots. So again, I find it much easier to deal with the horizontal stretches or shrinks by changing my scale and then just ignoring my new x values just by pretending that I'm drawing the graph the exact same way as normal. But then I did have that second shift of a vertical shift down. So that's why everything has shifted down a little bit in the graph. And that's it for how to graph tangent and cotangent graphs, both without transformations and with transformations. I hope that will help.